Okay, so today class we will prove a theorem due to Cartan-Serre that it claims that whenever you have a compact complex manifold, all the cohomologies with coefficients in coherent sheaves are finite, finite dimensional. Okay. I mentioned that in the case of locally free sheaves, you can prove this using this finiteness theorem of elliptic operators in a very similar way that we did with the Dolbeault cohomology groups when we proved this Kodaira-Serre duality. I mean, one of these facts in this result was the finiteness. But this is more general. And in order to prove this, we will have to use some functional analysis. So this class, I will spend a lot of time introducing or recalling some facts from functional analysis. Okay. Before doing that, I will mention something that I didn't have time to say the last class. So definition, an analytic variety X is holomorphically convex if for every k contained in X compact, it's holomorphic convex hull. So kx hat is by definition the set of points in X such that the uniform norm, the module of f of x is less or equal than the norm of f in this compact K for every holomorphic function. Okay, if this set is also compact. Okay, this is a result that I won't prove. It's also hard to prove, and sometimes you prove it in the course of complex geometry. So an analytic variety X is a Stein if and only if it is holomorphically convex and its global holomorphic functions separate points. Okay, this is a characterization of Stein varieties, and I won't prove it. This is a big result. I am mentioning it just to obtain the following corollary. So corollary. So if U and B contained in X are two analytic subvarieties of an analytic variety, which are Stein varieties. Then the intersection is also Stein. Okay, so the intersection of Stein varieties remains Stein. And it's clear just because obviously if the holomorphic function separates points on U and B, the restrictions will separate points in the intersection, right? And this holomorphic convex hull of any compact container in the intersection will be equal to, will be also, well, will be compact and will correspond to the same holomorphic convex hull, right? Than in any of these U or B, right? Will be also contained in U and B and will be compact. Okay, so in particular, so a remark is that in particular for every analytic variety, right? What? Sorry? Only one of them to be Stein. I'm not sure about this. No, yeah. I mean, the problem is not separating points. The problem is to prove that the holomorphically convex hull is the same in the intersection. What is contained? You have to prove that you can extend functions. The global functions can be extended in the intersection to the. Mm-hmm. Mm-hmm. The convex hull with respect to U will be compact. Yes. Okay. It's contained. Why is it contained? You're saying that? Yeah, it's true, right? You're saying that if, okay, you're saying that this is true, right? That this is contained in this, right? For every K contained in U intersected with V compact, right? So you have to prove that whenever you have a point that satisfies this relation for every holomorphic function defined over U intersected with B, then it also satisfies this relation for every holomorphic function defined over U. Yeah, and that's true, right? Yeah, I think you're right. Well, doesn't matter. The point is that the intersection of two Stein is Stein, or the intersection of one Stein with something. There is something that I don't believe about this. Well, okay. Doesn't matter. Well, the point is this. Okay, in particular, for every analytic variety X, so we can take we can cover it by Stein open sets and this will be a good covering, right? In the sense of Leray theorem. Right? And it will be a good covering in the sense of Leray theorem for every coherent sheaf, right, over X. Okay, so now the purpose of this class is to prove the following theorem. So theorem due to Cartan-Serre. We will do this in order to prove Serre-Gaga correspondence. This is an important piece of the proof, and well, we cannot skip it. So let X be a compact analytic variety and F any coherent sheaf then all the cohomology groups are finite dimensional. Okay, so in order to prove this result, we will have to use some tools of well, a theorem due to Schwartz about operators between Frechet spaces. And so I will recall all these definitions and results. So definition. So let E be a C vector space. Okay, a semi-norm over E is a function. So P from E to the non-negative integers such that it satisfies the triangular inequality and also it has an homogeneity property okay. So this is a semi-norm. Okay, Frechet spaces. Frechet space is a C vector space F together with a family of semi-norms. Sequence of semi-norms. such that it satisfies the following relations. So first, so if all the semi-norms vanish on a point of the vector space, then this point is 0. The second property is that if you have any sequence such that it is Cauchy for every semi-norm, then it converges. So there exists some point in E such that xn converges to x in every semi-norm. Okay, so it's kind of analogous to a Banach space, but with a lot of semi-norms. And the other properties is, well, it's superfluous, but is that the semi-norms are related. Okay, so this is a Frechet space. So in particular, this space is a metric space. It's a complete metric space. So, so the family of semi-norms this family of semi-norms, they induce a topology on F, right? And this topology is metrizable. Right, with the following metric. And it's easy to see that these properties implies that FD is complete. It's a complete metric space. Okay. Well, furthermore, the third property, so 3 implies that we have a system of continuous functions, right? So we have that F with Pn plus 1, the identity map is continuous, right? And so we have that the topology of F with respect to the metric or with respect to the induced by the semi-norms is the inverse limit of this system, right? Okay. Okay, clear? Yes. So an example, well, our example, the example we're interested in is the, so X Hausdorff, no, it's a locally compact second countable topological space okay, then the space of let's say C X C, right, and this the space of continuous functions from X to C together with the topology of uniform convergence in compact subsets is a Frechet space, right? And in order to see this, you just need to take the uniform semi-norm on some exhaustion of compacts, right? Of X by compact, right? Right? So this topology makes this space into a Frechet space. Okay? And in the case where, where X is a complex analytic variety, well, it's an analytic variety. This is the subspace of holomorphic functions, right? This is closed. It's closed under the topology of uniform convergence in compact subsets. So, in particular, is Frechet. Okay. Okay, so definition. Let phi from E to F be a continuous linear map between Frechet spaces so we say phi is compact we say it is compact if there exists some B contained in E open neighborhood, neighborhood of 0 such that phi of B is pre-compact. I mean, the bar is compact in F. Okay, this is a compact operator. And the theorem that we will use due to Schwartz is the following. So let E, F be Frechet spaces. phi from E to F a surjective continuous linear map, and psi from E to F a compact continuous linear map, right? Then the image of the sum of these two maps, right? Then so phi plus psi. So I will put it like this. The image of phi plus psi that goes from E to F is closed of finite codimension. Okay. So note that here I'm taking the sum. I mean, for every point in E, the value of this function at this point will be the sum of phi at x and psi at x, right? This is not surjective, it's just because phi is surjective, okay? I mean, if phi is surjective, it doesn't imply that this is surjective, okay? Okay, so and a reference for this theorem. Well, I think that this theorem might be very classic. Probably you will find it in a lot of functional analysis book. But I took it from this book, Goning, Rossi, Analytic Functions of Several Complex Variables. Okay, and this is in the Appendix B. Okay, no questions? Everything clear? Yes? Good. Okay, so, well, first of all, I won't give a complete proof of this result. This result is not that easy. And in order to give a sketch of proof, I will have to use some results. So the first thing that I have to prove is the following proposition. Proposition 1, let X be an analytic variety and let S1 to Sk be holomorphic holomorphic collections of P functions. I mean, P collections of holomorphic functions. Okay, P tuples of holomorphic global functions. Okay, then the submodule generated. So N, the submodule generated by them inside this space is closed in the topology of uniform convergence on compact subsets. Okay. Well, here I am putting this topology on each copy of the space of global holomorphic functions, and then you take the product topology. Okay. It will also be a Frechet space. Okay, this is the proposition I have to prove, and in order to prove this proposition, I will have to use some results about convergent power series that I won't prove, so I will just give you the reference. So in order to prove this proposition, we will need two lemmas which can be found. I mean, they are not so hard to prove, but you need to use this Weierstrass preparation theorem. It can be found in seminar Henri Cartan. Tom 4. This is exposition 11. And the name of this thing is annexed the series for this is by F. Bruhat. Okay, so the first lemma is the following. So lemma 1. So consider S1 up to Sk be collections of P formal power series in n variables with complex coefficients. Then there exists a C-linear, there exist K C-linear maps. So we have this lambda I that goes from this space to the space of formal power series. Okay, such that for every f in the submodule generated by them, f is equal to the sum from I equal 1 up to k of lambda I of f times Si. Okay, we have this lemma, and furthermore, this lambda I are continuous with respect to the topology of simple convergence of coefficients. Okay, and which is this topology? So definition. So we say that f, well, some sequence fk contained in C x1 to xn, the space of formal power series, converges to 0 in the topology of simple convergence of coefficients if whenever we expand each of these formal power series, so we'll have here I in, let's say, this to the how many variables n, you will have here a coefficient depending on I and k times the expansion, right, x0. So whenever we have the power series expansion, the k converges to 0 for every I. Okay, so this is the topology of simple convergence in coefficients. Okay, so this is the first lemma. And the second lemma is the following. So if S1, Sk are P collections of P formal power series, such that each of these formal power series are convergent, okay, then for every T that it's in the module generated by them that is also convergent, so whenever we have a combination of these convergent power series that might have non-convergent coefficients, but when the total sum is convergent, then these lambda i's of T are convergent. Okay, so this is the second lemma. But we have to, I mean, this means that whenever you have a convergent series belonging to the submodule generated by convergent series, then the combination can be taken with coefficients also convergent. Okay, so using this, the proposition is simple to prove. So the proof is, so we want to show that n is closed in the uniform convergence norm, right? So consider any sequence contained in n, right? That is this submodule generated by S1 up to Sk, right? Contained in and such that they converge uniformly on compact subsets to some t. Okay, and this is okay, and we want to show that this t must belong to n, right? So we, for every x in x, we want to show that tx belong to nx, right? This is what we want to show, right? Okay, and so how do we prove this? So since this convergence is uniform on compact subsets, it implies that we have also convergence as in the topology of simple convergence of coefficients, right? So we have that this Tnx converges to Tx in the topology of simple convergence on coefficients, right? It's just taking the derivatives, right? You're just taking a uniform convergence on some compact neighborhood, and then you have convergence of all values of the derivatives. And that's exactly the coefficients of this formal power series, right? So you have this convergence, and then by continuity of the lambda i's, you will have that the lambda i's associated to the localizations of these sections on the stalk, I mean. So these lambda i's of this Tnx will also converge to lambda I of Tx, right? Simply the simple convergence on coefficients, right? And so we will have that as a formal power series, we will have that T is equal to this sum, right? Tx will be equal to this. Yes. Right? This is just by continuity. Okay? But this will be a formal power series that is also convergent, right? So this is also an element of OXNX to the P. Right? And as a formal power series is in the ideal generated by this S1x up to Skx. Right, and so by the second lemma, this implies that these guys are convergent. And so we're done. I mean, this implies that Tx belongs to Nx. Right? Nx will be exactly the space of holomorphic functions that can be, holomorphic P functions that can be written as a combination of these functions times holomorphic functions. This is exactly the definition of NX, right? And so we're done. Right? Clear? Okay, so we have this first proposition. So the second proposition is the following. Proposition 2. Okay, so let X be an analytic variety. F a coherent sheaf over X. And so for every X in X, there exists a Stein open subset, there exists a Stein open neighborhood of X such that we have a short exact sequence of the form 0 n O x n to the P restricted to U and F restricted to U, right, of coherent sheaves. And also such that the global sections, n of U is finitely generated. Okay, we have this property, it's finally generated module, and so by proposition 1, so this subset will be closed in the topology of this space, of the Frechet topology of this space, and so we can induce a Frechet topology on F of U, right? We have an induced structure of Frechet space on F of U, right? And this topology is independent of such a short exact sequence. Okay, so this is the second proposition. Is it clear? Yes? So the point is this. We already have a Frechet space structure on the global sections of this sheaf that is just given by the uniform convergence on compact subsets, right? And we already proved that this subset is closed if it is globally generated by a finite collection of sections, right? This is what we prove in proposition 1. And so the quotient will be also a Frechet space, right? So this f of u will have a structure of Frechet space, and what I want to prove here is that this structure is independent on the way you generate f. Okay? Clear? Okay, proof. Okay, so first of all, to know that this neighborhood exists is easy, right? I mean, it's obvious that there exists some, the Stein open neighborhood will be a basis of the topology. So we will have this kind of short exact sequence just by the definition of a coherent sheaf, right? It will be coherent. And the problem is that to have that this space is finally generated in global sections, well, you just take the stalk at x, right? The stalk will be finally generated because it will be a submodule of an Ethereum module, right? And then you take these generators, and you know by Oka's theorem that in some neighborhood they will generate globally the submodule, right? So maybe you will take first an open Stein neighborhood such that you have this sequence, and then you shrink it in order to use Oka's theorem to have this second property. Okay? And you can shrink it in order to also be a Stein. Okay? So the first part is easy. So let us show the independence of the topology with respect to the sequence. Okay. Okay, so consider another sequence. So let 0, m, o, x, n, q restricted to u, f restricted to u, other sequence satisfying the same properties. Okay, so I will call this morphism here by pi, and this other morphism by rho. Okay. So again, since these open sets are, since this open set U is a Stein, we know that the H1 of M and the H1 of N are 0, right? Because it is Stein. And so this sequence will remain exact in global sections, right? So let S1 up to SP be the global sections of F in U, given by Si will be the image of EI, where these are the canonical generators of this sheaf, right? Okay, and let T1 to TQ the images of rho of EJ, right? These are the same thing, right? The canonical generators. Okay, so we know that we can write, for instance, each Si as a combination of these other guys, because this sequence remain exact on global sections, right? So it will be from j equal 1 up to q of some alpha ij tj, right? Where these alpha ij are holomorphic functions on each u. Right? We know we can do this. And so we have a map, an induced map, by this collection of functions. And so we have, so this alpha ij, they will induce a map that will go from Oxn P of u to Oxn Q of u, right? And we'll take any family here, Fi, to the family sum. I mean, for every, let's say, Gj, that it will be equal to the sum over I of alpha ij Si. No, Ei. Alpha ij, what is the map? Fi. Right. Right? We have this map. And obviously, it is continuous with respect to the uniform topology, the topology of uniform convergence on compact subsets, right? So which is continuous. Right, and so if this map is phi, and also we will have that phi composed with, I mean, it's rho composed with phi is equal to pi. Right? This is also trivial. Okay? And so whenever you have a, so which one is it? So whenever you have an open set of f of u, which is open in the topology induced by rho, it will also be open in the topology induced by pi, right? Because the preimage of this of the open set under rho, and then the preimage under will be open. The preimage under phi will be also open by the continuity, and so it will be an open set in the topology induced by pi, right? So this implies that the topology induced by rho is contained in the topology induced by pi, and so by symmetry they are equal, right? Clear? Okay. So the third proposition that I have to prove is the following. So let X be an analytic variety and F a coherent sheaf let U and B open sets, so small enough Stein open sets. So the first part is that Well, let's put it. So first, so if B is contained in U, then the restriction map is continuous in the topology induced by proposition 2. And the second part is that if B bar is contained in U and is compact, then the restriction is compact. Okay. Proof. Okay, so the first part is almost trivial. So you know that in order to induce the topology on f of u and f of b, you have to take a sequence, right? A special sequence, right? So take the sequence satisfying the hypothesis of proposition 2, and obviously it will remain exact when you restrict it to B, right? So obviously it will give you also a good sequence when you restrict it to B, right? So the topology of f of B and the topology of f of U is induced by the same sequence, right? And so in order to prove that the restriction is continuous, you just need to prove that the restriction here is continuous. And that's obvious, right? Okay, so we just have to check the second part. So we take B compact, B bar, B pre-compact. And we have to prove that this restriction map is a compact operator, okay? So we have to produce a neighborhood of 0 in the sections of f of u. Well, again, since we already have this, the topology of f of u and f of b is induced by this map, it's enough to show that the restriction on the level of AP of xn is compact, right? Again, it is enough to show that this restriction is compact. Okay, and in fact, this is enough to show that it's compact just for one copy, right? And how do we do this? Just consider the following neighborhood. So W will be the set of functions such that the norm, the uniform norm of f in B bar is bounded. Okay, this is obviously an open set in the topology of uniform convergence on compact subset, right? This is a compact subset, and this is the uniform node, right? So this is an open neighborhood. Of 0. And its image is just its restriction to B, right? And its image to B is pre-compact by Montel's theorem. Right, Montel's theorem is a consequence of Arcela-Ascoli theorem, and it says that a collection of functions in the topology of uniform convergence in compact subsets is pre-compact if and only if it is locally uniformly bounded. Right? For every point, there exists you take a compact neighborhood, and it has to be uniformly bounded. Okay? And this is obviously globally uniformly bounded, right? So it is also pre-compact. Okay? That's the proof. So the time. Okay, so now we can prove the theorem, proof of Cartan-Serre. Okay, everything is clear? All the propositions? Everything clear? Good. So what's the proof? So first of all, let U I and I be a countable open covering of X given by small enough in the sense of proposition 2. Stein open sets. Okay, we can always do this since X is paracompact, right? So we can take this kind of covering, and so on every CQ of UF, we have an induced Frechet structure, right? Frechet space structure. Right? This is because the covering is countable, right? This is a product of countable copies of Frechet space, right? So we have an induced Frechet structure. Okay. And furthermore, the check differentials they are continuous, right? By proposition 3, right? right? So in particular, we have that the space of closed check cochains, it is closed in the Frechet topology, right? So this C, Q, UF is closed. And so Frechet. Right? Okay. So consider now B equal to a set of Bi with I and I, a refinement given by the same indexes, with the same index. Such that Bi bar contained in Ui is compact. So this R compact is small enough Stein open sets. Okay, so we take a refinement in this way. We can do this because it is locally compact. So you take the refinement, and then we will consider the refinement map, right? Right? We have this refinement map, and we know that this map is an isomorphism. Right? This is Leray's. Right? By Leray's theorem, this map is an isomorphism. Right? And so this implies that CQ of B F is equal to the image under the refinement of the closed Q cochains of U plus the exact cochains, right? Right? This is the surjectivity part of this isomorphism. Right? You have this equality. Okay. So now consider, so let E be the direct sum of these two spaces, CQ UF plus CQ minus 1 BF, right? So this is a Frechet space. This is also Frechet. And consider the following functions. So now you have here E, you have here the first projection to CQ of UF, the second projection to CQ minus 1 of BF, right? And then compose this with rho UB, right? That will go to CQ of B of F, and compose this with delta, right? Right, so we have these two maps. I will call this map psi and this beta. Right, and we know they are continuous, right? They are continuous by everything that we did. I mean, proposition 3, right? We know that this is continuous, we know that this is continuous, this will be continuous by the definition of the topology on E. So these two maps are continuous. And so suppose now, and also we will have that if we define phi to be the sum, right? That goes from right. This map is continuous and surjective. Right, by this. Okay, so now suppose X is compact. So we can take U finite, right? Right, so since they are finite, this map psi will be compact, right? Because it will be it will come from it will be the restriction of some other compact operator, right? It will be compact on CQ since it will be a finite product of compact. It will be obtained. I mean, the CQ will be a finite product of this Frechet space, right? And each of these copies will be compact, right? And so this guy is compact. And so we are done. So by Schwartz theorem, we have that beta. So beta that is equal to phi minus psi has a finite codimension. Right, and the image of beta is exactly the image of delta, right? So this implies that HQ check P of F is finite dimension. This is isomorphic. Clear? Questions? Okay, so this result, we will need it in order to prove Serre's Gaga correspondence. And in fact, we will prove the analogous result also in the algebraic category, and it's much easier, you will see. In general, all these theorems in the algebraic side are much easier than in the analytic side. And that is why Gaga is so powerful. Gaga enables you to prove theorems on the analytic side by proving them on the algebraic side, in the case of projective or complete varieties. Okay, no questions?